Wow, that was really, really cool. I need the audio from whatever they used for that. So next up, we're gonna have a panel called the Path to Synchronous Composability. So what I'm gonna do is use my ultimate stage powers to start bringing people up here. Some people would say I'm drunk with power. I would say that, oh, I put Bobbin in there. Nope, sorry, Bobbin, not this one. Someone would say I'm drunk with power. As it turns out, yes, I am, and no regrets on my end for that. All right, awesome. So we're going to go ahead and take the slides down. Thank you all for joining us today. I'll go ahead and just say everyone's name. Zaki is here. Brendan is yet again moderating. Ilya is from the Near Foundation. Sriram is Eigenlayer, and Ben is from Espresso. Oh, and I didn't even mention Zaki is Occlusion and like 19 other projects. So anyway, welcome, and we'll just take it away from Brendan.
I did not realize that I was moderating this one as well. If I was unqualified to moderate the last one, I am surely unqualified to moderate this one. But it's really, really nice to have so many people that know far more about asynchronous and synchronous composability than I do. And so I'm just really excited to speak with all of you. Maybe we could do a round of intros, starting with Sriram.
Hey everybody, I'm Sriram. I was formerly professor at the University of Washington, Seattle, and I run a project called Eigenlayer, which allows anybody to stake and use the security for arbitrary new protocols.
Awesome. And then Zaki probably needs no introduction, but can give one anyway.
Sure. Zaki, co-founder of Occlusion, DeFi protocol called Sommelier. I've done some other things.
Cool. Ben?
Yeah, I'm Ben. I'm the CEO and co-founder of Espresso Systems. We're working on shared sequencing and base rollup solutions for sharing liquidity across chains. So this is a very relevant panel.
Cool. And then, yeah, last but not least, Ilya.
Hi, I'm Ilya, co-founder of Near. Near started as asynchronous sharded blockchain and now pioneering chain abstraction.
Awesome. So I think that's a good way or a good place to start. Maybe we could go through and each of you could just give your view on the necessity of synchronous composability. I think we'll have some like maybe differing views, but Ben, I know that Espresso is super focused on shared sequencing. One of the superpowers of shared sequencing is enabling synchronous composability in different forms. And so maybe you could just give your view on synchronous composability, whether it's required and like what it provides.
Right. I mean, I think synchronous composability is, maybe the holy grail or far end of the composability spectrum. And there's also forms of composability that are not perfectly, what we might call synchronous composability, which are already useful. But in general, the value, I think that the value of Ethereum is the fact that it is one system, and the fact I think the value in any blockchain is its global scale. The fact that if you build an application and I build an application, these applications can talk to each other, and that's very much what distinguishes it at a user level from Web 2. I mean, of course, there's a security element as well, but in terms of the utility of Web 3, it's been the fact that it can get so many different people to trust one system where all these different applications are pluggable with each other. And so if we're trying to scale blockchains, we want to retain that utility. And synchronous composability is the holy grail of composability. The idea that a single transaction could do things in your application and my application that are all dependent on each other. It could move assets from one to another. We could do things like flash loans, etc. But there are also weaker forms of composability that are already very useful.
Okay, maybe Zaki, do you have a view?
I wanted to go do something first, which I would think we should try to define synchronous and asynchronous composability without assuming anyone knows what we're talking about. Maybe I'll give like a concrete example of these things. So synchronous composability is like anytime you let's say you like they're like, let's say you've used Instadep. Instadep is a great example. Synchronous Composability app. It has these things called zaps, and you can take a position like move from, let's say, like lending on Aave to I don't know, the eigenlayer deposit contract in like one transaction, and it'll swap for you through Uniswap. And the whole thing will atomically succeed or fail, right? So you get this property of like atomicity, and like it's very familiar to every crypto user. Like you do your transaction, you get the transaction ID, you plug it into Etherscan or another block explorer. It gives you maybe a comprehensible error message if it didn't go wrong, but this is your user experience. If you've used something like Squid Router or like ibc.fun in the Cosmos ecosystem, you'll have like the experience of async composability. So there's like a set of transactions that get strung together. Maybe you don't have to do all of these transactions yourself. We've gotten better at that, but they could fail independently. Like you could start an IBC transaction, but it could time out in the middle, or there couldn't be enough liquidity, and your coins might not return to like the blockchain you started out with, but they might end up on like another blockchain. So this is like the common experience of these things. So earlier work, I worked on a asynchronous composability system called IBC for several years. It's widely deployed. It moves billions of dollars. Then I worked on a multi-chain DeFi system called Sommelier, and I don't want to go into the details of it, but it does very sophisticated things. Like our vaults are like the biggest liquidity provider for wrap staked ETH today, and it's like this complicated cross-chain system that does it. And at the time when we started building it, we could only have thought of building something like that on Ethereum synchronous. But just in the last week, we launched on multiple L2s with Sommelier. And then soon we're going to have vaults that actually share liquidity between L2s. And we thought when we started, we didn't know how to do this, but we're 2 years into having these things, to working on this project. And we were about a year into being in production. And as we've gotten more experience, we've actually learned how to deal with asynchrony pretty well. Now we have to cobble together these systems. Like our cross-chain system has IBC, Axelar GMP, CCIP, and intents in it, which is kind of ridiculous. But that part of the process is like more painful to us than asynchrony at this point.
Mm-hmm. That makes sense. Yeah. It's a good starting point with definitions. Sriram, how do you feel about synchronous composability?
Yeah, Zaki defines synchronous and asynchronous composability. I'm going to go down one more level and just define composability. The thing is, I think there are different, when we're thinking about composability, I just want to bring back one aspect, which is what is the trust model for composition? And there are many different trust models that one can think about when you're composing, which is using multiple systems together. And the weakest trust model, or the starting point of the trust model, would be something like, I have 2 domains and I want to kind of do actions on these domains, or 2 applications and I want to do actions on these 2 applications. Each of them, maybe they're living on a chain. So, and to compose this, now I'm using a third actor called a bridge. And the bridge is now helping me move information or assets across these 2. In this model, now the trust is the worst of the sending domain, the receiving domain, and the bridge. And then you can go to one level, a trust minimized, which would be then say, oh, I don't have an intermediate actor, and IBC is like this, which Zaki and others pioneered. And IBC is like, oh, if both the domains are safe, then your transactions are safe, right? So you don't need to rely on a third actor. And so in this kind of like a composition, the trust assumption is that this might happen. So the trust assumptions on composition are in a separate dimension from synchronous or asynchronous composability. So I just want to kind of bring out this dimension here. And in something like IBC, you're basically trusting both the domains to be safe. And then when you compose across multiple apps, you may be taking trust assumptions across many, many different trust zones. So you are only as secure as the weakest of the trust zones that you're touching. Now, what is even more trust minimized than this is to have, if all of these different zones are identical, if they all depend on exactly the same trust assumption, then the weaker of all of them is still the same thing. And that happens when, for example, you have things like layer 2s. You have layer 2s on top of a common blockchain, then they all move together on a common underlying substrate, and they're all verified and validated together. And what this does is to provide trust minimized composition, or you could say trustless composition. Basically, all of them are correct or and validated, and there is no way for the systems to desynchronize. So normally when you think of like composing, you have this problem that these two zones, you can think of them as two trains kind of running in parallel tracks, these two chains moving along. And when one of them, on a bridge is basically like this like rigid thing connecting these two like moving trains, right? And what could happen is one of them desynchronizes, which means they fork, or something happens, then the rigid object connecting it can just break. So that's a kind of a mental model for the trust model of using a bridge to compose between these two. Something like layer 2s on top of a common substrate is basically you have a train, and inside that there are many like people sitting, or like many boxes, and all of them kind of move together. They cannot desynchronize. And so this is just a hierarchy of trust assumptions when we are thinking about composition. And I think this is a completely different axis than the time scale of composition, right? And the time scale of composition, Zaki already defined synchronous, which is actions happen simultaneously, atomically together, or don't. And this itself could require additional trust assumptions, right? So I will have atomic composition if ABCDEFG holds. So just, the temporal axis and the trust axis, two different axes that we need to think about when you're thinking about these systems.
Yeah, I think that's a really good way to put it. I mean, certainly it's how we see the ag layer, is like, how do we ensure safety and preserve, in some sense, this trust minimized property while massively reducing latency and creating the ability for atomicity. And so yeah, I mean, not to shield Polygon stuff, but that vision is like, it is possible in conjunction with things like shared sequencers, like what Ben's working on with relays and builders. And so but yeah, this panel is not about Polygon, it's about you guys. And so Ilya, how do you see, obviously like Near is very focused on asynchrony, and I think that you, maybe more than anyone else, have seen sort of like the limitations and the pitfalls of synchrony and sharding and locking, and sort of like the cost that some of these systems or assumptions impose. And so it would be really good to get your view on asynchrony and synchrony and trust minimization.
Yeah, I think maybe a good way to describe it is kind of, if we take Ethereum, right? In Ethereum right now, every transaction stops the whole world. It's pretty much like when transaction arrives, everybody's like, okay, everybody stop. We're going to process this transaction. This is the most important thing. And then, okay, let's move to the next transaction, right? And, there's 100 gigabytes of state. All of that state is locked, even if this transaction processes and touches like one smart contract. Now, Solana introduced this idea that actually, if you mark up on your transaction which pieces of state you're going to be executing on, you can lock only that state, and then so you can, in theory, process in parallel a bunch of stuff. And there's like techniques how to do it on EVM now, but that kind of was the original idea. Is like, if you know what you're going to be touching, you can lock only that state, and then you can use the fact that you have lots of cores on your computer and process things in parallel. So you can still have, in a way, the same kind of level of composability, even though you have kind of parallel computing. Now, the challenge was that you still are limited by what one computer can do. However, kind of powerful computers are now, it's still kind of, okay, let's stop the world and process all the transactions that we can on one machine. And so kind of our assumption has always been, right, if we are bringing billions of users, there's no single computer that will be able to process that. There's no single computer that will be able to even store all of the state and transactions that are kind of needs to be processed. And kind of, the way this is usually dealt with is by parallelizing the execution, by parallelizing the state, and it's called sharding. Now that is naturally requires some mechanism of kind of figuring out how to process things in parallel and maintain consistency. And we have now a spectrum of approaches, right? There's an approach of Cosmos, which is like, hey, let's just have everything is an independent chain, and they all kind of fully asynchronous, and there is a message passing protocol to synchronize kind of when you need to communicate. You have indeed rollups, which described, which is kind of like, we have like a base synchronization base, but they're still running in parallel and like firing in parallel. And because right now, at least, the current frameworks all have very different kind of approach to how proofs are settled. Like the actual, like we have this kind of lots of like, oh, can I settle actually this there, or I need to wait 7 days, right? And so there's like few approaches like Agglayer and Fast Finality, we're working with Eigenlayer to actually synchronize that more and give you this like some framework there. And then the Near's approach, kind of from where we started, was, well, can we have kind of the same thing? Like if you have, every smart contract, every account actually has independent rollup, but we synchronize them every block. So we kind of communicate and synchronize every block. And so because of this, we can do message passing and can do all of the things kind of embedded into the system itself. And you still have this asynchronicity from perspective of every independent account, a contract, you send a message to somebody else, right? It's all like, because they are running on different computers, but now you have some guarantees about message delivery, consistency, and kind of all of these things. And so that's kind of the spectrum, right? And I mean, it's really cool to have all of these options, because there is like different cases when different of these options are needed. And in turn, you get like everybody's working on the trust minimization on the other side, right? Where like, Cosmos has also, how do we do shared security? Obviously, Ethereum with rollups, but also with Agglayer, like how do we do shared security, kind of faster finalization, and then Near kind of provides it on the base layer. But I think the biggest benefit, though, coming back to what Ben mentioned, is like we can rely on using other applications without like, if you usually in Web 2 use something and it's built by two people in a garage with a dog, like you're probably not going to build $1 billion business on top of it. But in crypto, you can actually do that because you have this kind of trust minimization. You have, kind of smart, how the smart contract will execute and run. Now, there's a lot of caveats on all of this, right? The upgradability, the kind of what is the trust mechanisms between in all of this. But I think that's the biggest benefit that we're getting in crypto. And so like for me, composability is the biggest benefit we have in crypto and in Web3. And we need to promote that, and then just give as many tools as possible to developers to really like connect these things together.
Yeah, I think that's a really nice way to put it. I'd like to change gears slightly, and you mentioned, Ilya, like sort of some of the instances in which synchronous composability imposes costs because you're sort of reliant on a single machine, and you have to take locks. And one thing that Justin and Ben helped me understand and learn about is sort of this, I would say this new paradigm where we kind of apply proposer builder separation to shared sequencing. Like my naive view of what shared sequencing was okay, we have some committee and they process all the transactions and they order them, and that's actually not really the vision for shared sequencing. It's we have some committee and they auction off slots to super professionalized, like high capacity builders. And so these builders can be running in data centers. They're not really constrained computationally, and they can actually coordinate synchronous composability across many different chains and domains. And so, Ben, I think you're sort of the best person to like dive into that vision and talk about sort of that view where we don't really give up decentralization, but we highly leverage centralization to provide synchronous composability.
Yeah, I think that one way to think about it is that in any consensus protocol, like there's two parts, right? There's a proposer, which is acting, at least for a moment, as a very centralized entity. And it's the one that's like basically doing the execution for everything in this blockchain and creating a proposal. And then the security of the blockchain comes from the fact that you have testers, which are stamping their approval of what the proposer did. And this is going to ensure that the blockchain doesn't equivocate. So whatever was proposed doesn't get changed later. And in some cases, it's also doing verification, although one way to think of rollups is that they like massively distribute the process of creating the information that is needed to verify what was in a proposal. And that information doesn't need to be re-executed and verified by everyone. So with shared sequencing, we should think of it as, there's another mechanism for basically determining who is this proposer. I mean, even if you have rollups that are each running their own thing, if they each have a decentralized protocol, it could be the case that there is one proposer who just tries to be this proposer for all of these different rollups. And in so doing, it's able to create an economic surplus because it can do things that other proposers that are not coordinated wouldn't be able to do. And so a shared sequencing mechanism can be re-envisioned as a shared mechanism for, in the most economically efficient way, determining who gets to be the proposer for producing and sort of coordinating between rollups in each slot. And this doesn't have to be fixed forever. It can be dynamic. And we can think of it as a marketplace whereby rollups are effectively selling their block space through this marketplace to bidders who are trying to become a shared proposer. Maybe not for all chains, but for a pair of chains. And so that's, I'll pause there, but that's sort of the way that I think about it.
Yeah, I think that's like a very compelling vision, because we can have I think in the world where we don't make usability trade-offs, or we don't sacrifice like the experience of using a single chain, even in this multi-chain ecosystem, like we need probably a decent amount of synchronous composability. And I think that this view is one where we can actually have that at scale without giving up things like security or decentralization. Obviously, I think that there are maybe some trade-offs, and maybe Zaki or Sriram can speak to those. But I think, like, for me personally, it's like a very cool view, and one that's like really complementary to what we're trying to achieve at Polygon.
I find this vision like very intriguing. Like, it's very, very intriguing, because the trade-off between like big, like large fat blockchains, like the sort of monolithic blockchain thesis, right? Is like, yes, you're going to go and do most TPS as fast but maybe the need for synchronous composability, or like the economic surplus of synchronous composability, like where is it that like it was just massively more capital efficient to be able to synchronously compose than it would have been to have to asynchronously compose these systems? Maybe those things are not routine. Maybe those things happen infrequently. Maybe, someone trading NFTs over there and someone having a perp dex over here, like those things don't need to interoperate very often. And there's very reasonable, and there'll be like a lending market and a spot dex, and like these things can be independent. And there's lots of opportunities, as I think we've seen a lot of experimentation in various ecosystems around like optimizing for these things, or we see a lot of perp dexes in Cosmos these days, and their need for synchronous composability is infrequent. if not non-existent. So the idea of having, of getting to a world of this, like, where you have these, like, where you have this marketplace for block space and you have this, like, ad hoc composability, it does seem it does seem like a way of having our cake and eating it too. My only caveat of it is that, like, these systems tend to be very complex. They tend to be very complex relative to, like, sovereign asynchronously composable systems, or like sharded asynchronously composable systems. And I think, like, the biggest open question is whether or not that economic surplus is large enough to justify the technical investment needed to, like, bring this sort of ad hoc synchronous composability world to life.
Yeah, I think that's a fair characterization. I'd be curious what Ben and Sriram and Ilya think about this, but I do think that the nice thing about this vision is that it degrades sort of gracefully. Like if something goes wrong with the builder, or there's like some issue with the complexity inherent in the system, then I do think it sort of reverts back to functioning without synchronous composability. But I really like what you said about like monolithic chains, and the way that I sort of describe it or like to think about it is like Solana is a monolithic chain, not to pick on Solana, but on Solana you have like on-chain games that are contending for shared resources with like dexes and flash loans, and it does seem like there's like just this inefficiency that's inherent in that design, where like those games are like paying for synchronous composability in some sense when they truly don't have to, because they don't need to be like so closely located in the sort of composability space to DeFi primitives that like actually require composability and but yeah, I on the question of like complexity and how this vision like holds up when things go wrong, maybe Sriram and then Ben or Ilya, I'd be curious about your views on this.
Yeah, I will stick to my dimension trust. So when we are thinking about synchronous composition in a system like what Ben just described, which is builders basically coming ad hoc and aggregating multiple block spaces and producing blocks simultaneously. So when we think about trust here, it's always the question is trust for whom? And to think about it from an end user point of view, let's say I want to make a transaction which is synchronous across 3 chains and atomic. And from my viewpoint, transactions should only fail if these 3 things happen together. Now, again, we can start seeing there is a nice trust spectrum here. The first kind of like a operating point here would be something like, or the builder makes a promise that they are going to make sure that these transactions all happen together, right? And this would be the first, most trust requiring type of atomic composition. Okay, I trust the builder. The builder promised me, like, they're going to do it. Okay. Then you can go like one level up and then say, no, actually the builder has already staked, for example, a certain amount of economic capital, made an assurance that if I ever break my promise, so they make actually credible commitments on chain using something like Eigenlayer, make a promise that I'm sticking to my promise and I won't break it. And if the amount of economic capital that is at stake is higher than the amount of economic value that can be extracted from breaking the promise, then you can assume that they'll be honest, and even if they're not, you can slash them and redistribute the money to the injured users. So that's another kind of level up on the trust assumptions. The highest grade of this trust assumption would be something like the ag layer that Polygon's building, which is now, when you're making commitments to each of these chains, I actually acquire a lock and submit a ZK proof that I've actually held. So it's basically just the same thing, which is credible commitments, where you make a credible commitment a priori. But the commitment is enforced cryptographically rather than cryptoeconomically, which is what something like Eigenlayer would do. And I think that kind of like sets the kind of trust spectrum here, which is you have this zone, the different zones of operation, which may be different layer 2s, for example. And then what happens is that each of these come together on demand, ad hoc, to when there is the economic surplus that Zaki was pointing out. And they come together to make blocks, and it's justified because the cost of making these blocks actually together is worth it, right? For whatever other reason, because at that time there is enough interactions. The really nice thing, I think, from my point of view on this is that it is a much more like bottom-up, design where you don't have to coordinate a priori. You can coordinate a posteriori. Like when the events to actually coordinate arise, you can actually coordinate them. But you should have made some kind of pre-arrangement on the coordination mechanism. Otherwise, you will not be able to coordinate post hoc. Just adding one more kind of dimension here, which is the near finality gadget, for example, that we are working together on. The idea there is, either with the in any of these methods, one of the things that you absolutely need is that when you make promises that these are the blocks that need to be built, you should not be able to build some other blocks, directly by bypassing that system. So you need a lock that, when you've sold the blocks that you're actually kind of building in this order, they actually get built in that order. And I think, there are different ways and different layers in which you can express it. And I think that's, with the nearest finality layer that we're working together is basically just a layer which gives this assurance that, yes, this is the order in which it will be returned there. And, you cannot bypass this thing. So, yeah, so that's my quick trust assumption overview on synchronous.
Cool. Maybe Ilya, anything to add there?
Yeah, I think to kind of add to Zaki's point, the complexity here is because you have a lot of moving parts that require pretty much kind of building another blockchain, right, to coordinate that. And that's why, what Shiram was describing, if you want this kind of commitment that this multiple of these rollups will include something, like for them to actually commit to that, they need to use something where they will be enforced to not be able to publish alternative block, right? Then that system itself can actually accept the shared transactions that will go into all of them, because like that enforcement can happen there. And so you're moving very clearly toward still having like a blockchain that coordinates all that, and how exactly you design that blockchain is obviously various design decisions, but it becomes that okay, well, now everyone who wants to opt into this, right, they need to pretty much use this blockchain to see if somebody bought the space from them, include that. That should be kind of the the prefix of the block, for example. You need to have an ability to enforce the execution itself, because the really important part to understand is that EVM is not designed for multi-chain. I think that's a kind of really important. And what it means is that, let's say you want to do a flash loan between two different chains, just the address space, your message dot sender, all of those things don't work really well, right? And so if you want to do actual synchronous composability between these two domains, you need to have somewhere not just execution, but you need to provide back the outcome of this execution. So you need now to have this sequence, the sequencers that presumably, if we have it opt-in mode, right, they need to have their own sequencing plus an ability to accept somebody else's not just sequence but executed transactions with commitment and with presumably proofs that this is a correct execution, right? So there's like a lot of kind of component need to go into this, where, you know, the alternative is you just say like, okay, we'll sell the whole block, and they just kind of load up us again with the full execution proof, with state witnesses and kind of all of those things to like include that. And so all of that is just like super complicated, and kind of you end up in a way going closer and closer to building like a kind of a blockchain that you wouldn't need the rollups in. And maybe there's an architecture that is more like optimal for that. So like on Near, for example, a lot of the pieces of designs of standards are designed to be multi-chain. So like our token standard is multi-chain by definition. For example, contracts like Uniswap is able to receive messages from other chains, because on Near, any other contract in a way is another chain. And so you need some of those details as well for this to truly work in kind of a more, like I would say, simpler way. And I would say with a current EVM implementation, it will become super complicated, and we'll have like collisions of addresses and other things that you know, potentially people will exploit.
Interesting. I'm not sure I agree, but Ben, maybe you have a different view on like the sort of complexity and just like how difficult it is, how complex it is to move to like a PBS plus shared sequencing system.
Yeah, I mean, I think what Ilya is talking about is more about the EVM itself, and whether the EVM itself is set up to just receive messages from each other if you have different instances of the EVM. So I guess what I'm going to comment on is less specific to this. I'll let you guys have that debate. And more about just, you know, what is the technical complexity of this coordination layer that I'm talking about. And so if you think about rollups on Ethereum, I mean, they already are coordinated through Ethereum, right? The model is already that you have Ethereum as a coordination layer. And so the question is simply, how do we improve on top of this? Right? The solution we have at Espresso, and it's not that it doesn't have technical complexity to build, but it's still within, you know, this same model of you have many different rollups and they just share some common infrastructure, just like they share Ethereum for data availability and settlement. They can share a mechanism through which we decide, and it's a consensus protocol, right? The results of auctioning off proposer rights for chains. So this is a consensus protocol that also provides what Sriram was talking about of finality over the results of not only who is given proposal rights over different chains, but what they proposed in such a way that they cannot equivocate. And so you could use Ethereum for this. You could, in a very naive way, just use every Ethereum block to, you know, record this. It would just be less efficient. And so that's why at Espresso we have a BFT side protocol that is used in order to determine the outcomes of this, and we allow the L1 proposers to simply participate in this protocol on the side, and this uses eigenlayer restaking. But you know, ultimately you do need to design some kind of, again, just to summarize, you need to design some kind of coordination layer. You need to have consensus among the rollups on what was the result of this auction, which rollups are proposing for themselves, which rollups have delegated their proposal rights for a given slot to a shared proposer, and what was proposed. What ended up being proposed. How can we prevent equivocation on what was proposed? That's fundamentally what is required here.
Yeah.
I think maybe because I totally agree with that, and that all makes sense. The question is, how do you go from there to actually synchronous composability of two, for example, EVM rollups, right? And
right.
I think
So
where it's complicated.
yeah, and so that's where, as a special example, if there's a proposer for two different chains, let's say they're within the Polygon ecosystem, then this proposer for those two different chains can now, using the ag layer design, start, as it's constructing the next blocks of both of these chains, can queue messages and pass messages between the chains and create proofs and then aggregate them at the end. And that's why ag layer beautifully fits in with this model. This model provides an ad hoc coordination layer that enables things like ag layer. I think though, Ilya, I think that, and correct me if I'm wrong, but you're sort of pointing to, okay, how do we actually design the two chains to receive messages from each other and pass it between applications? And then are there, is the EVM really, designed well to do this? How complex is that?
Well, I would say what you described is perfectly fits with a synchronous composability that, for example, Near is well doing. But when you say something like, I think people expect, let's say just flash loans as like a canonical example of this. And so you can imagine, if you have a flash loan on one rollup, and then you're trying to swap that flash loan, for example, you're doing like a triangular rebalancing, right?
Mm-hmm.
You're trying to swap on the other one. You need to overlay pretty much the balances of the account that don't exist on that chain, right? And so now if you have you need the machinery on the other side to know how to deal with pretty much non-existing balances.
I don't think that's necessarily needed. Like, for example, in the 3 trust models, the simplest trust model is you trust the builder. The builder actually has awareness of both the chains, and the builder is basically like taking the risk and actually doing the atomic swap. You go one level up, the builder can put up more than enough cash on as to the flash loan and actually go and execute it. So the chain's state transition functions are themselves unaware of this like external complexity. But then the ag layer design would be that, just to finish this, the ag layer design would be that the two chains can make progress only if the blocks are simultaneously valid. And so that would basically make it that when you also know that there's a joint builder, then you get exactly the atomic composition feature that you want.
Just this builder is building for both rollups. It's building the next block for both rollups together. It's executing for both chains. And it's simply that the extra complexity is in the fact that you can't just make a contract call from a contract on one chain to the other without passing a message that has a proof attached to it. And that's where the additional complexity comes from.
Yeah, so we did get the 1 minute warning, and so I don't want to cut anyone off without like an outro, but maybe we'll just go really quick, like 15-second closing thoughts. Ilya, starting with you.
Yeah, I would say because we kind of, I think Shiran touched on it. I think there is a approach of intents where as a user, you describe the intent and then you have the block proposers, builders, searchers, whoever else figure it out how to deal with it and not actually needing to figure out how exactly transaction is routed across many chains. And I think that is how we're going to get to the kind of, from a user perspective, what users looking for in synchronous composability. And then all of the technology we are all building here is infrastructure behind the scenes and users just saying I want this, figure it out, swap between 15 chains if you need to. And so that's kind of what we're working on, this chain abstraction. So I'm inviting everyone in Denver to join Chain Abstraction Day.
Awesome. Shout out to Chain Abstraction Day. Sriram.
Also such a good name for the concept, chain abstraction. I go back to the dimension I was always talking about, trust. When you're thinking about composition, we need shared trust, we need cryptoeconomic trust. That's what we're building at Eigenlayer. So any of you want shared security or economic trust for doing any of this stuff, feel free to reach out to.
Cool. Ben, any closing thoughts?
Yeah, I think just to coming back to this, the importance of coordination and the fact that coordination will happen anyways. So we should design around it in a way that it's, done to minimize risk, because if we have more risk and lack of coordination, it is going to lead to more centralization and pitfalls for users.
Completely agree. Zaki, any closing thoughts?
I think this was like I think this is like a kind of a good survey of the like issues that like things like the abstraction layer, chain abstraction, asynchronous composability protocols, like trying to have like native interoperability more widely in the L2 world are all trying to like get at, and it's like we're all trying to kind of figure this out together. I think it is probably the most exciting thing happening.
Awesome. I agree. That's a great way to end it. But thank you all very much for being here, and yeah, thanks for the really nice conversation.